networks, they may not be so simple. That is, directly we use V is equal to IR and get the answer. We could also have arrangement like this, where if someone asks what is the current in this circuit, that is what is the ammeter reading and in which direction the current will be flowing, the things they may become slightly difficult to find out. In cases like this, when we have a slightly, you can say, complicated cases where we cannot use directly V is equal to IR and get the answer, over there Kirchoff laws given by Gustav Robert Kirchoff in 1882, they become quite useful. We come across Kirchoff laws in radiation also, but right now we are bothered about the Kirchoff laws in current electricity. Kirchoff had given two laws. One is Kirchoff current law, the other is Kirchoff voltage law. So we have two laws. One is, we can say, Kirchoff current law, and the second is Kirchoff voltage law. So when we talk about the Kirchoff laws, we have two rules or two laws. One is Kirchoff current law and the other is Kirchoff voltage law. Kirchoff current law is also known as the junction rule or node rule, and Kirchoff voltage law is also known as mesh rule or loop rule. These two laws or rules, they are based on conservation of charges and conservation of energy. When we say KCL, that is Kirchoff current law, that is based on conservation of charges. That is, at any node, at any junction, what's the total current is coming, the same current should exit. KCL stands for Kirchoff current law and KVL stands for Kirchoff voltage law. When we say KCL, that is Kirchoff current law, that is also known as node rule or junction rule. And when we say KVL, Kirchoff voltage law, that is also known as loop rule and mesh rule. Kirchoff current law is based on the conservation of charges. It means if we have any junction, whatsoever the current is coming towards the junction, the same current should exit. It means if 1 ampere current is coming over here, 2 ampere is coming over here, 3 ampere coming over here, so all the currents they cannot accumulate. I is dq by dt, that is current is rate of flow of charges only. So primarily when we talk about current, it is, we are indirectly talking charges only. So no charge can accumulate over here. Whatsoever charge is coming over here, the same charge should move away from this junction. So it means 1 ampere is coming over here, 2 ampere is coming over here, 3 ampere is coming from here. So 3 plus 2 plus 1, 6 ampere is moving towards the junction. So from here the current should be in this direction and that should be equal to 6 ampere. That is primarily Kirchoff law. Similarly, if we have, let's say this is a junction, we have 1 ampere over here, 3 ampere over here, 6 ampere over here. And we have to find what is the current in this wire. So we say that is towards the junction, it is only 1 ampere, whereas 6 plus 3, 9 ampere is moving away from this junction. The total current which is moving towards the junction, that should be equal to the current that should be moving out of the junction. So this is 6 plus 3 is moving away from the junction. So moving towards the junction should also be 9 ampere, but we have only 1 ampere. It may rest 8 ampere. In this, it should be 8 ampere in this direction. The other variation of KCL is, we can also say, suppose this is I1 is here, I2 is here, I3 is here, I4 is here. One of the ways, that is how we say Kirchoff current law, is we can take the currents which are moving towards the junction as positive and moving away from them as negative on the basis of conservation of charge. Then it means I1 plus I2 plus I3 plus I4 is equal to 0, and if we take that is towards this as positive and away from this as negative, so it takes the form I1 plus I2 plus minus I3 plus minus I4, as I3 and I4 they are going away from junction. So that once again our common sense, I1 plus I2 is equal to I3 plus I4. That is the total current. There is no accumulation of charges over here. There is no accumulation of current. So whatsoever the current is approaching the junction, the same current should be moving away from the junction. That is Kirchoff current law. Let's say these wires, they are the part of bigger network, and the currents in the wires, they are shown like this: 1 ampere, 2 ampere, 2 ampere, 4 ampere, I and 2 ampere, and they are shown with a direction also. We have to find what is the value of I in this part of the network. So here if we see, we can start with any junction, and the simplest junction is, one is, we can see over here, that is 3 ampere coming from here, 2 ampere coming from here. So if we take this as junction, so 3 plus 2, 5 is coming over here, so 5 ampere should be moving out in this direction. So if you look over here, this is simply a wire only, that is this 5 ampere is coming over here. On the conducting wires, we can always slide. So whether we join it over here or we join it over here, that is one and the same thing. We have not done any changes. We are not jumping any circuit element like resistance, etc. So these are perfectly conducting wires. So whether you join it over here or join it over here, that is one and the same thing. So this makes our job much easier, because now we see that is 5 ampere is coming towards it, 2 ampere is going this way, 1 ampere is going this way. So total is 2 plus 1, 3 ampere is going away from this junction and 5 ampere is coming towards the junction. So now the total current which is moving towards junction is greater than the current which is moving away from the junction. So it means that is in this wire the current should be moving away from this junction, so as to make total current which is moving away from the junction is equal to total current which is moving towards the junction. So this is 5, 2 plus 1, 3. So this should be equal to 2 ampere. So this makes 2 plus 2 plus 1, 5 ampere is moving away from the junction and 5 ampere is moving towards the junction. Now 2 ampere is coming over here, 4 ampere is coming over here. So if it is 4 plus 2, 6 ampere is moving in this direction, 6 ampere comes over here, 2 ampere is coming from here. So it means the direction of current, if you say that is, it will come out to be negative, or if you have to find simply what is the direction of current in this. So 6 ampere is coming from here, 2 ampere is coming over here. The total current which is approaching the junction is 6 plus 2, 8 ampere. So the current should be over here, 8 ampere. If the direction is given as over here, that is, someone says what is the direction of current, so we'll say that is I is equal to minus 8 ampere. Or if we say the current is in this direction, we simply say that the current is 8 ampere in this direction. So this is how we can use the junction rule to find the current in the various arms of a bigger network. Now let's apply KVL, that is Kirchoff voltage law, in its simplest of the forms. We have taken a very simple network where we can find the current through directly using Ohm's law also, but let's use KVL to understand it. So when we have to apply KVL, that is Kirchoff voltage law, loop rule or mesh rule, what we do is first we look out for any closed loop. So this is a closed loop. This is the only loop we have and this is a closed loop. We do the naming A, B, C, D. This is naming is done. And now we take a loop over here, A, B, C, D, A. We start with A and finally we have to close the loop at A only. So this is the one point you have to take care of. Let's say we have taken the current flowing in this direction and say the current is I. So obviously over here we say that there is a single loop, so the current is going to be only in one direction and there is going to be one value of current only. But let's see how we apply KVL. We start from A, this is I only, and over here that I comes and I comes back into the battery. When we say we are moving in the direction of current, it means we are moving in the direction of conventional current, and conventional current is positive current. So when we are moving in the direction of conventional current, there is a loss of potential. And in the battery, suppose we are going from negative terminal to positive terminal, so we are gaining the potential. When we are going from positive to negative, there is a loss of potential. So when we start from here, A to B, when we go, so we use Ohm's law, I into 3, that is 3 into I, there is a loss of potential. Losses, they are taken as negatives. So minus 3I. We go in this direction, once again there is a drop of potential. So once again there is a loss. Minus 2I. We come over here, we are going from negative to positive, so there is a gain of potential, plus 20. Please see that this is also in volt, this is also in volt, this is also in volt. V is equal to IR, and this is once again V only, so we can easily add and subtract. They are not the different physical quantities. So when we come over here, then the potential difference between this point and once again this point is obviously going to be equal to 0. We have closed the loop, we have come from here to here to here. Now this is loop, and that should be equal to 0. Conservation of energy principle, that is, finally we are saying the potential difference between this point and once again we reach this point, that is equal to 0. We have closed a loop, we have taken a closed loop, and we are saying finally when we reach over here that the potential difference V is equal to IR plus this, that should be equal to 0. So when we say this is equal to 0, so this is minus 5I plus, so this is minus 5I plus 20 is equal to 0, or 20 is equal to 5I. So I is equal to 20 by 5, that is 4 ampere. If we use directly Ohm's law, we know that is 3 ohm and 2 ohm. These two resistors, they are in series. We can simply add them up to get a total resistance, net resistance of the circuit as 5 ohm. Battery has a voltage of 20 volt. So when we use V is equal to IR 20 by 5, that once again it should come out to be 4 ampere. We have not done this to find the value of I. We have primarily done it to understand how to apply Kirchoff voltage law, how to take the closed loops, and in the direction of conventional current there is a drop of potential. When we go from negative to positive potential, there is a gain of potential that is going to be taken as positive, loss of potential that is going to be taken as negative. Once we understand Kirchoff current law and Kirchoff voltage law, now we are ready to move to slightly more complex networks.